Okay, should we start? So before we move on, are there any questions? Things will get slightly more formal. I already apologize that there'll be a little more formula, so don't be too scared. So if at that stage it's pretty clear, so I'll just start from where we were and show you now really in practice the city int version. So I will focus on that specific algorithm. And so the starting point of these Quantum Monte Carlos is, again, the action. Okay, so I wrote this earlier. The action of the Anderson impurity model is something which is minus the integral. So this goes from 0 to beta, d tau prime. There's a sum over spin. So I have to apologize. I think I used D dagger for my impurity level, but I'm so used to write C's that if I start with D, I'm sure at some point C's will appear. So I switched to C already now so that you're gone. So it's C sigma. Larger than this? Okay. So let me put a bigger G. Like this, and a C tau prime of sigma. So this, if you want, is the non-interacting part of the action, and to that I have to add the interaction, which is U integral d tau. This is from 0 to beta, n up times n down. So this is my Coulomb interaction. Okay. So the natural way to cut this into two pieces, in that case, because we want to do perturbation theory in U, is to take this as being some S0, which was my SA. I'm putting 0 here to emphasize the fact that this action, S0, this first term, is describing my non-interacting system. Okay, this is why I'll call it S0 rather than SA. Okay, this is to keep in mind that it's non-interacting. And then I have the second term, which I'll call SU, which is that's the U term. Okay. So now if I go back to the last equation we had before coffee break, so the point was to compute the partition function. And so Z was something like Z0 times sum, this is my perturbation expansion, sum over n minus 1 over n factorial, like this. Okay, and then I had the average value of SU to the power n, and I'll put the 0 here to emphasize the fact that I'm trying to take the average value in the non-interacting system. Okay, so I'll do one more step, and I'll show you a little problem that we have. So what I have to do is take this SU, basically this term, and feed it in there. So what I get is Z0, this sum of, I end up with minus U to the power n factorial. Okay, this is the U that was here. And then I get all these integrals that fall down. Okay, so given that it's to the power n, I will have n of these integrals that show up here. So I'll write them as d tau 1 to d tau n. These are my n integrals in time. They all go from 0 to beta. And what I'm left with is an average value of all these operators here. So there's n up, tau 1, n down, tau 1, and so on until n up, tau n down, tau n. Okay. So if I had to stop here, I mean, I would, in principle, immediately stop here and not even go on. I want to do this part of the sum, these sums here, by Monte Carlo. Okay. Now, this guy here, is the average value in the non-interacting system of some n that multiply each other. This number is positive. Okay. This thing is positive. This guy is alternating sign at every different perturbation order. There's this minus 1 to the n. Okay, so at every different perturbation order, I get contributions which have a different sign. So this is going to give me a huge sign problem. If I keep it like this, it will just never work. Okay, so at that stage, one can even stop. I mean, it's not useful to go any further. So one has to think a little more about how I could escape the sign problem. And thank God there are guys that are quite clever and Ruptov, well, maybe some other people before him, but really came with a nice idea to rewrite the interaction Hamiltonian slightly differently, and this will completely save us. Okay, but you'll see. Well, one has to think about it. It's not that obvious. So my interaction term, remember, is just u. I'll write it simple, and up and down. Okay. So now I'll try to rewrite it slightly differently. Okay, and see if this helps. So I'll write it u over 2. I'll call it n up minus some alpha up times n down minus some alpha down up. I'll add a second term here, which is similar, n up minus alpha up down. I'll give you the definition of these alphas in a second, like this. And the alphas are given by this. So alpha up, up. Same thing as alpha down, down, which is 1/2 plus some delta. And the off-diagonal alphas are alpha up, down, same thing as down, up, which is 1/2 minus delta. All right? Well, you'll see by doing this. Okay, if I look at purely n up and down terms, I have u over 2 here, u over 2 here, so I'm indeed getting this guy here. Okay. Now the thing is, I'm adding new terms like that multiply n up. N up is multiplied by alpha down up with a minus sign, and by alpha down down. So the prefactor of n up is the sum of these two guys. If you look at it, it's 1, okay, because the delta cancel out. Okay. So with respect to this, I have an extra u over 2 n up term, okay, which I will have to correct. So I'll correct it. Actually, the same thing happens with n down. So I just add this little extra term. And I'll let you check that these two things are the same up to just a constant. Okay, there's an extra constant which appears here. It's a function of the alphas only, okay, and u, of course, but there's no operator in there, so this constant, it doesn't matter, okay? So I haven't done much here. All I did, I rewrote the interaction term, okay? This is now my interaction term, the new one that I'll use from now on. So this is my interaction term. And this goes into S0. Okay, this is not an interaction term. It's just a linear term in n. Okay, actually, if you look at it, all this really does, it shifts the chemical potential again. Okay, so this term, it goes in S0, and it really redefines a new chemical potential, which is the original 1 minus u over 2. Okay. Actually, this is very close in spirit to the IPT, where I had to remember to shift my G0 by u over 2. Actually, to a quite large extent, it's the same story. Okay, so this really goes in SO. So I'll rewrite what I was studying here, but now I'll write this new interaction term instead of just u and up and down. That's the trick. Quite a clever trick, because it completely gets rid of the sign problem. Yeah, so I'll come back to this, but yeah, maybe I can answer already now. So here, none of what I wrote depends on delta, because everything cancels out. Okay. What does depend on delta in the end is the sign. So delta will be a control parameter to control the sign in the end. I'll show you this in a minute. But yes, actually delta changes several things. It's not a completely innocent variable. It has influence on the way the Markov change evolves. So on the one hand, it controls the sign, but it also controls the average perturbation order. So actually, it modifies the weight of some configurations, and by changing delta, you might change actually the speed of your algorithm quite a lot. And often, it's a trade, this delta, because when you give it values for which the code goes fast, then the sign is a little worse. If you give it values for which the sign is good, then it's going slow. So you have to find somehow an optimal delta. Okay? But that's the key. Right? So let me find another chalk. There's a constant which shifts the overall Hamiltonian, but this cannot change the physics, right? Okay, so yeah, I just kept it away. Doesn't matter. Any other questions? So, all right. So I'll do exactly the same thing, but of course now the terms will change a little, but I'll keep. So now the partition function is again Z0. Okay. To write this slightly differently, because I don't want to carry these two terms, I can just write it as u over 2 sum over some auxiliary variable, which I call sigma. And so I can keep just one term, is n sigma minus alpha sigma. What am I doing wrong here? No, it's n up. So, sorry. N up, alpha up sigma, and down minus down sigma. Okay. Sorry about this. So I'll just add this extra sum to avoid carrying out, these two guys. Okay. So when I plug this in the partition function, basically I'll get again n of these integrals, but now I'll get also n of these sums over sigma. Okay, because my interaction term has this sum over sigma, and I'll get u over 2 instead of u. So I basically get sum over n. It will be minus u over 2 to the power n, 1 over n factorial. And then I'll get n of these integrals over d tau, sums over sigma I to sigma n. These are the n sums over sigma that come from there. And eventually I have this average value to compute, which now is slightly different because it involves stuff like n up at time tau 1 minus alpha up sigma 1, n down at time tau 1 minus alpha down sigma 1, and so on, all the way to tau n and sigma n. Okay, a small difference with respect to here. Now you see, things have changed quite a bit. So alpha, if I take delta small, say, and I just look at these first terms here, okay? This is essentially minus 1/2, n up minus 1/2 times n down minus 1/2. Okay? You can see that if you want to keep your density fixed, so if you say n up plus n down is something fixed, then the product of these two things is actually negative this time. Okay? At least you can always find a delta for which the product of these terms is negative. Okay? It's a hand-wavy argument because really one should take the quantum average, but okay, the overall idea is nevertheless that we're in a completely different situation here. We had something which is definitely positive. Here, because there's this minus alpha, okay, you can show that there's always a delta for which this will become negative at some point. Yes? Well, yeah, sure, but it's just, so it's minus 1, but this comes, there are a certain number of copies of this guy. So at order 2, it's minus 1, so it's positive. So it has, in the end, the same minus 1 to the n sign as this. And this is how you cancel the sign problem. Okay, so this is quite a clever trick, but it works. So I'll do one last manipulation here, maybe. So let me erase this. Is to get rid of the one. Well, sorry, there's obviously something I forgot. There's a time time order product, which I forgot here. So this is T ordered, sorry. Sorry about this, I tend to forget this guy. So these operators, they need to be time ordered. Sorry, it's not the last mistake I make, so be ready. So you see here all these tau 1 to tau n integrals, they all run from 0 to beta. Yeah. Okay, well, it's sort of a, the point is here, n was a positive number between 0 and 1, say. Okay, so obviously, I sort of make a classical kind of argument because, this average value is not the average value of n times the average value of n and so on. So what I'm saying is, they're operators, so in principle, I cannot do what I'm doing now, but just to give you an idea. So this is between 0 and 1 and so on. So they're all positive, so in the end, the thing is positive. Fine. Here, because imagine I'm close to half filling, okay? And I want n up plus n down to be 1/2. And I want to analyze this thing, n up minus 1/2 times n down minus 1/2. So if this is equal to 1/2, so this might be a little bigger than 1/2 and this a little smaller. So if this is a little bigger, this guy is positive, this is negative, the thing is negative, okay? And this is true for all values that these guys can take as long as, Now obviously the argument is hand wave because this is not true, of course they're operators, but the idea is basically this, right? You can show it a little more formally actually. Any other questions? Yeah, it's 1. Yeah, sorry, it's 1. I meant 1, but it's still, yeah, if one is a little bigger than 1/2, then the other is a little smaller than 1/2. Sorry, the sum was 1. Other questions? What's that? What triggers this kind of idea? Well, who knows what happens in a Russian's head? I mean, how do I know? No, I mean, before adding the little delta, writing the Hamiltonian as something like u over 2 times n minus 1/2 times n down minus 1/2, this is quite natural if you want to enforce particle symmetry. So writing the Hamiltonian like this without the alpha makes some sense. And actually, you can start with this. Okay, so you can really start your perturbation theory by not putting the 1/2 shifted by delta, but really by putting 1/2, exactly 1/2 in there, okay? And you can look at the atomic limit, for example, where everything can be solved exactly. If you do this, you can prove and see that in that case, there's no sign problem, okay? The only problem is that there are, from one perturbation order to the other, there are huge variations. So if this is exactly 1/2, and you look at the atomic limit, the contributions at order 1 is 0. The contribution at order 3 is 0 exactly. At order 5, it's 0 exactly. So this causes some ergodicity problems because I cannot start from 2. I'll never reach 4 because I have to go through 3, which is exactly 0. Okay. So the delta is here to give some probability to these guys so that I can move around. Okay. And this is things that you can prove in the atomic limit. And then okay. So it's yeah. But still, I say yeah, you have to think about it. Okay, so the last little move here I want to make is about the 1 over n factorial. So all these integrals of tau 1 to tau n, they run from 0 to beta. Okay, but actually, if I pick 2 of them and I exchange them, I permute them, okay, they will permute here as well. But because they're time ordered, in the end of the day, they'll end up in the same position, okay? So permuting 2 taus here, in the end, this correlative, it will be the same because it's time ordered, and because they appear in pairs, you won't get an extra sign when you reshuffle things in the good order, okay? So by avoiding all these permutations and taking directly here an integral where tau 1 is from the beginning bigger than tau 2, bigger than tau 3, you know. I'll avoid, I mean, I'm sampling only a smaller part of the subspace. And actually, to get the full one, I have to take n factorial times this guy, okay? So this cancels this term. So this is quite a nice way to write things. You don't have this 1 over n factorials. Here, you keep your d tau 1 to d tau n. The sum over sigma 1 to sigma n. And okay, let's see what to do with this. So this is a correlator that you have to compute in your non-interacting state. So who knows Wick's theorem? Okay, so I think you'll have to take my result for granted, but there's a very strong theorem, which is really the starting point actually of building a perturbation theory and the diagrammatics, is that there's something very special about the non-interacting ground state, basically about Fock states. There's something special because computing averages of such a correlator, which is an endpoint correlator, you can always rewrite it as the product of Green's functions which only involve one-point correlators, okay? It's a very powerful theorem, which I would never be able to show you quickly like this. It takes quite a bit of time, so you'll have to take that for granted. Vijay will probably do it in 20 minutes, but it would take me a day or two, probably. So thanks to this theorem, which is called Wick's theorem, you can basically rewrite this long correlator as a determinant, okay, which is called d up. So one other thing which you can do in the non-interacting system, up spins and down spins are not correlated, okay? So I can really write this thing as the average value of the up guys times the down guys, okay? So I'll cut it into two pieces. So there's a d up, what I'll call d up, and a d down, okay? And the definition of d sigma is it's the determinant of a matrix which has on the diagonal terms which are G0, well, we'll have enough space, I guess, which are G0 sigma at time 0 minus, imaginary time 0 minus, minus alpha here, sigma 1. This, you get these terms on the diagonal, okay? So it's the sigma 1, sigma 2, sigma 3, and so on. And everywhere else in this matrix, you get G0 of sigma of tau 1 minus tau 2, tau 1 minus G0, tau 1 minus tau 3, and so on. Same thing all over. Yeah, sorry, this is a bit not super straight. Okay, so you see, basically, this average value ends up being a determinant of a matrix whose entries are essentially the Green's function, the non-interacting Green's functions, G0 taken at the time tau I minus tau j. The only exception being on the diagonal where the alpha come back, okay? And you have to take G0 at time 0 minus, okay? That's what you have to remember. So you see, when you compute this determinant, it ends up being the product of Green's functions, okay? So you can always write such a correlator as the sum of products of Green's functions. So that's Wick's theorem. Okay, so take it for granted, but it works.
Maybe this is not timely, but if I go to the high version of this is the expansion, then I don't have Wick's theorem, no? Because
no. So yeah, Philip will show you that in the other case, indeed, the starting point is the atomic limit. And the atomic limit, unlike here, is not expressed in terms of a BCS wave function or of a Fock states. So there's no Wick's theorem in that case. So there you will have to compute the trace.
I will do this on Thursday.
Okay. So Thomas will, yeah, of course, you'll do this in many more details. But nevertheless, by shuffling things around, there will eventually be some determinant coming up too. But that's a different story. It's not Wick's theorem. Any other questions? So you see, you were pretty much set. This is my Z here. This is the weight that I want to use. I will have to, by Monte Carlo, I will have to do the sum of perturbation orders, the sum of all these imaginary times, okay? And these are continuous variables. So this is why you get this CT QMC, okay? Because I will really do the Monte Carlo over this continuous set of variables here. And there's this sum on sigma, which sort of introduces auxiliary spins in my system. This is somehow the price to pay for having rewritten my Hamiltonian in this nice way there, okay?
Sorry, so you say it's continuous, but it still has the symbols like tau1 to tau n.
Sure, what's continuous is the tau1 takes values which are continuous between 0 and beta. Of course, I have a finite number of these guys because at a given perturbation order n, I only have n of these guys, but n will run to any order. So there's no truncation in the perturbation order n.
I mean, I'm just trying to compare it to the Hirschfeld. You also make slices, but slices are in beta.
In Hirschfeld, in a certain sense, even though it's not really the same thing, but in a certain sense,
You have a slices in beta.
you have slices and somehow n is fixed. So the number of auxiliary spins is fixed. But here there's no constraint. So it's like if, well, it's a little bit like doing Hirschfeld, but letting these things move where they want. Well, it's not really this, but you know, the idea is more or less this. And what's nice about this is that the power behind this is that it will actually go look for the most relevant perturbation order. And sometimes it turns out that this average perturbation order is actually a lot lower than what is needed, really, even in Hirschfeld. And this is why it's faster. Good. So let me tell you how we'll do this Monte Carlo then. I have to check. Time a little. So what I'll sample really is some sort of
You need a Weeks theorem for that, right?
So what I'll try to sample is really just this ratio z over z0, which I call z tilde. I'll tell you why I in a second why I pick this as what I sampled. But anyway, so I'll compute this by Monte Carlo. So the sum over x that I've introduced in the Monte Carlo, namely the x I'm talking about, this sum is now the sum of the perturbation order, my n d tau integrals, the n, and the sum over auxiliary spins, sigma 1 to sigma n. These are all the sums I have to carry out by Monte Carlo. The weight, I mean, so x, yeah, this is where I talk about configuration. So x, if you want, is a set which is described by n, my tau i's, and these sigma i's. Okay, I can write it like this in a short form. So what we'll do is give this set sort of a graphical representation. Okay, so it's sort of an easier way to see what are the different things, what are the different configurations. So the way to describe this set is to simply take an interval between 0, between beta and 0. I mean, I start with beta because there's time ordering, so that bigger times go on the left. And then I'll put vertices at different places, at times tau 1, tau 2, tau 3, and so on. And I'll draw some auxiliary spin on these guys, and this gives me the value of sigma I, which is either plus up or down, okay, and so on. So you see, by doing this kind of drawings, I essentially completely determine all this. I count the number of vertices. There it's n. I look where the tau i's are and the direction of the spin. Okay. So in Monte Carlo, we always have a tendency to draw things, okay, because we like to see these configurations, okay. So this is why I always confuse variable and configuration. Okay. Now the probability of a given configurations of P of x, well, it will be this, basically, times these two determinants. But I'll have to take the absolute value. So it's u over 2 to the power n, d up, d down. Okay, so that's the weight I'll consider. So I'm essentially set. I mean, I know what I have to sum over. I know the probability. All I have to decide now is how I'll do this Markov chain, right? How do I generate my configurations? So I'll do Metropolis. So eventually with Metropolis, I will know if I have to reject or keep my proposals. But I still have to decide how to make these proposals, okay? So the moves are really simple. There are two moves. There are moves which are insertions, which mean that I start from a given configuration. This is, if you want, my X. So my X has vertices in some places. Okay. And what I'll do is I'll start from this, and I'll insert a vertex somewhere randomly. So I pick a time. So I pick a random time. I add a vertex, and I pick a spin either up or down, and I add it to this configuration. Yes?
So comparing with the expression that you have written when you were discussing about the algorithm, you've written summation over x, p of x, f of x.
Right.
So f of x here is just 1, right?
I'll come back to this. Eventually, what I want to measure, what I want to get out of the algorithms of this is G, is the Green's function, and I'll show you. But I didn't want to make it in the beginning because it might be a little obscure. You can write G as exactly something which is this times the weight times something, which I'll give you afterwards. But I'll come to this later. But we use, in this algorithm, we use the components of the partition function to decide how to travel in configuration space. But then what we measure is something slightly different. It's a Green's function, so it means there will be some extra term. But I want to do this in a second because it's not so easy to get it. And the other move is just the opposite move, is removals, which, this is, so I have configurations like this. I just pick one of the vertices randomly, chance 1/3 here. I kill one, and I'm left with a configuration like this. So you see, ergodicity is trivial, okay? If I want to go from any configuration to another, I just remove vertices until there's nothing, and I add them up again until I get what I want. Okay, so ergodicity here is trivially proven, okay? Great.
So, for example, the Isaac model is a critical point. Now, single split flips won't do well, so you have closely correlated some, various algorithms.
Yes.
Are there some similar extensions of these kind of things?
Yeah, sure. Yeah. Actually, in this algorithm, it's not that useful, but one thing so they're called global moves. So what Vijay is referring to is, I'm not obliged to just do local moves like I do now, namely just changing just something, a small thing in my configuration. Nothing forbids me, for example, in a spin system, if I have islands of spin that go up and islands of spin that go down, there are these moves that say, okay, I'll choose an island where all the spins are up and I'll flip them all down. Okay, this is a slightly more sophisticated move, and it turns out that this is extremely important to be able to describe the system when the correlation lengths start to increase. In this case, a global move that you might want to implement, for example, is taking all these auxiliary spins and flip them. So take all of these and flip them, all of them somewhere else. But you can come up with all kinds of moves. You can also choose, for example, not to change the perturbation order, to take a vertex and just move it somewhere. Okay, so just do a move of a vertex. You can be willing to put 2 vertices at a time, and so on. Actually, in the algorithm, Philip will talk about these kind of moves are actually very important. For example, if you want to study superconductivity, you need moves that are a little more sophisticated than just purely local moves. Okay? Yeah, that's what I'm saying. You could very well just take a vertex and decide to make a move which moves it somewhere else. It turns out to be quite an inefficient move.
But that is actually equivalent to removing one and then
exactly. This is why it's useless to do. I'm also summing over n. Yes, sure. So Well, I mean, I'm not really shifting them, but like we said, I mean, at a given order, I could remove a vertex, go to order n-1, and add it back up somewhere else. So it's just like I had moved it. So eventually, I'm still sampling all possibilities, right? Well, I mean, you will answer this question in the tutorial on Thursday. No,
numbers and produce a corresponding configuration.
sure. I mean, what the computer gives you is a way to generate random numbers. So there's a way to generate a number between 0 and beta. That's not a problem. Okay, so this you can get. Now how you code this is, well, you know, there are many ways to do it. A way is to use a table which is a list basically of the different times, and for every time it tells you what the spin is, and you keep this list somewhere in memory.
So what are we saying? That for our problem, the important configurations are the one which we want to generate efficiently, and the other important unimportant ones we want to just discard or something.
Sure, there are lots which are very unimportant, but that's the whole point about the Monte Carlo. He will go choose the ones that are important. I don't know which ones are important, but the Monte Carlo, the important ones are the ones that are going to have a large weight here, and this is where you're going when you sample. You know, your probability distribution is centered around things which are heavy, right? So it will. You start from low perturbation order. The Monte Carlo will insert a certain number. And then at some point it will stay, for example, around the perturbation order, which is the more significant one, and it will just move around this. So that's the good thing. I mean, the Monte Carlo is working for you.
No, but where does the where does the intuition go in? Like in choosing the moves or in choosing the initial state?
Or the intuition, where it goes in that case? Yeah. Well. In that specific case, there's not too much intuition to have, because the configurations are, you know, it's kind of simple. So there's not really that much intuition you can have. In Phillips' algorithm, you'll see that there you can guess that on physical grounds that some configurations are going to be really bad. And for example, you know that if pairs of operators are too far away and U is large, you know this will be a bad idea because it will cost a lot of local energy. And so you'll try to generate things by putting these operators close from the beginning. In that case, I think there's no so obvious argument on what configuration is bad just by looking at it. Thank you.
So if you think in terms of doing usual perturbation case, like for example in a dense Fermi gas, we have some RPA. If I stop at the second order, I'll get everything divergent. But when I do an infinite set of diagrams, then I get some finite answer.
Yes.
So you may think that at every order there are important diagrams of maybe some quantum process, and somehow that is not coming up here.
Well, I mean, first of all, you're probably thinking at 0 temperature.
Yes.
So at 0 temperature, this diverges. The average perturbation order goes to infinity. So the thing works only because I'm at finite temperature, and at finite temperature, it looks, I mean, it turns out that important configurations are centered around some perturbation. But it's been known, and I think this is also why people haven't tried this before, because people knew that at 0 temperature, these series are ill-defined, that they diverge. So this is why probably no one has tried that early. This is why it's not, like we said, it's good not to know too much. Because you're unbiased.
So you also choose insertions and removals in your step, whether you will do an insertion or a removal.
Yeah, it's part of the probability. So as you start, the first thing you decide is usually with probability 1/2, of course. You choose will I remove or insert something, and then you move on from there.
If you know that the important processes come from some nth order, so restricting it to some n+5 or n+10 or something would give you essentially the same answer.
Yeah, if you could, yeah, sure. If it turns out that all of it is contained between 0 and 6, and you can carry out, but you can't, I can tell you, carry out the perturbations here up to order 6, then you're fine.
Okay.
But already, computing order 4
Oh.
numerically is, I think the best you can do is order 8. And you have to read by Monte Carlo, by the way. Because Genia Kozik, he goes up to order 8, but it costs him a lot of sweat.
One also has to worry about disconnected diagrams. One has to throw them. If in that determinant I have some disconnected Feynman diagrams, do I have to care about them, or?
No, you keep all diagrams. So the determinant is actually a family of diagrams.
Mm-hmm.
Okay, and you keep them all. There are disconnected diagrams in there too. So yeah. So you're not computed log of Z in that case. No cluster. Okay, so let's see, 40. So I'm not going to make this in details, but I'll still write it down. So for the insertion, okay, basically what you have to compute, so this acceptance rate here, to go from some x to some y, this is minimum of 1, and ty goes to x, sorry, this is y, p of y divided by t, x goes to y, p of x. Okay. So that's the thing which you need to compute at every step. For your insertion, you need to compute this to decide whether you accept the move or not. So, well, actually, I think we can compute it better. You see, the insertion is, you just pick in this direction. So the probability to go, the transition probability to go from x to y. Okay. This guy downstairs, well, I start downstairs, never mind. Is basically, I need to pick a random time. Okay, this comes with probability 1 over beta. And then I have to pick a random spin. This comes with probability 1/2. The probability of x, okay, which is, I'll say that this is at order n, okay, I'll have to put some, this is order n and this is order n plus 1. Well, the weight of this diagram is u over 2 to the power n, yes, and then there's the determinants and the up, the down. And I'll put a parenthesis here with n, just to remind that this is the determinant of an n by n matrix in that case, okay? Now the opposite move, to go from y to the other one, the transition probability is to basically, I need to go from here to here, I need to pick this vertex. This comes with probability 1 over n plus 1, simply. Okay. So this is just 1 over n plus 1, and the weight is u over 2 to the n plus 1. And again, 2 determinants, but this time it's an n plus 1 matrix. Okay. So that's the ratio. So things will cancel out, hopefully. They should, at least. Yes, so the 1 over 2 comes with n plus 1, like here. So this guy will cancel out. Okay. And so I'm basically left, so u to the power n leaves me just a u here. So basically this I can write as the minimum of 1, and it's beta over n plus 1. And then there's u. And there's the ratio of my determinants. These guys at order n plus 1. These guys at order n. Sorry, I think this is probably too small, but okay. Yeah, that's fine. Okay, so you see, at every step, at every move, at every insertion, you'll have to decide whether you accept the move or not based on this ratio here. Okay, and this is where the computational complexity comes in. Okay, because, okay, getting beta, u, and n is sort of easy. But this, in principle, I have to compute these full determinants here. N plus 1, sorry. Now this is an n+1 times n+1 matrix. In principle, I have to compute the determinant of this matrix, right? Same thing here and so on. If I really had to compute the determinant from scratch at every time, it would be a huge problem, okay? But it turns out that there are very simple formulas to compute this ratio, namely the determinant of a matrix divided by the same matrix which has just a removed line or column, okay? So these matrices are almost the same, there's just an extra line and column, and there are what's called Sherman-Morrison formulas that allow you to compute this quite quickly, actually at order n squared, okay? So you can do it pretty quickly. So you do the same thing for the removal, this is just for completeness. And then I'll, okay, not doing too bad. So the removal, so there it's the minimum of 1, and we'll try to get the same things. So now it's sort of the opposite. So upstairs, it's the transition probability to go from this to this. Okay, so this is at order n. This is order n minus 1. Okay. So this comes again with probability 1 over beta, 1 over 2, u over 2 to the power, what is it in that case, n minus 1. And my determinants up and down come at order n minus 1. The move in the other direction is picking with probability 1 over n one of the vertices, and it comes with u over 2 to the power n and determinants at order n. Okay. I'll let you simplify, but okay, I'll let you do the simplification. But that's all the ingredients you need to do your Monte Carlo, right? You start from an empty configuration, no vertices. You start inserting or removing vertices. You recompute at every time these ratios, decide if you keep or not the configuration, and this will span the whole set of configurations in this partition function. So the last step, and this is what you were asking earlier, is, okay, now I also want to measure something, okay? So I'll just give you, and I think I'll just give you the formula for G. So what you want to measure is the Green's function. From that you can extract with Dyson's equation the self-energy. So I'll show you how these weights are useful to compute the Green's function. So are there any questions at that stage? Sure, you could start from a configuration which already has a set of vertices.
So how do you choose? So whether to insert or remove? Because you opt for which one?
I don't choose. So I choose randomly between the two options. So if I have a configuration, the first decision I make randomly is whether I'll remove something or add something. And I do this with probability 1/2. Okay? So either I remove, or I add. Once I take this decision, I look at the configuration, and if I have to remove, I pick one and I remove. If I have to insert something, then I pick a time and insert a vertex. Okay, these are more technical details, but of course, I think we'll talk about it in the tutorial. But like I said, the probability distribution, it goes stationary after some time. So the question is, after some time, okay, how long do I have to wait until my Markov chain really produces something which is distributed according to the stationary probability? And so you have to wait a little, and this is called the thermalization or the warm-up of your system. And so you have to let in the beginning some time to your system so that it thermalizes to the correct probability distribution. But this, then you have to decide how long you wait.
And how do you converge, or how do you check for convergence? That means whether a move, that means which n, that means how to check the convergence.
So the way you check, okay, there's never really a convergence in these algorithms, in the sense that you let it run, and you let it run very long, and you'll measure something, for example, the Green's function. There will always be statistical noise in that Green's function. So the result you get will always have some statistical noise. So the length of the simulation decides how big or small are these error bars. So then it's your take to decide how long you want to wait or how small you want your error bars. If you're interested in simple quantities, you might allow for slightly larger error bars, and so you can make your simulations shorter. If you want to do some analytical continuation to get some real frequency data, you know you will need extremely small error bars, and you'll have to wait a lot longer. So it depends what you want to do with the data.
You don't have to see acceptance ratio or something like that.
No, the acceptance, I mean, a posteriori, the algorithm can tell you how many of your proposals were accepted on average, okay? If this acceptance is really, really low, okay, it means that what you suggested as new configurations was really bad. So then you can also think more and see more, maybe I should be more clever in proposing new configurations, okay? But in that case, you don't have, not so many options, so.
There are no parameters which check the acceptance ratio. Like delta,
No.
as you said, there are some implications of delta on some other than sign problem.
There's autocorrelation. So in a Markov chain, there's one configuration is quite closely linked to the other, okay? So this is something you can measure, but you can also measure it on the fly. It's not that easy, but you can. But you can do what's called a jackknife analysis, which tells you by looking at the quantity, you need to measure something actually to do this. But it looks at what you're measuring, and it can tell it can give you the autocorrelation length. So it can tell you, okay, it will take 100 Markov chain moves before you really get independent configurations. So you can do it on the fly, but in general, what we do is we measure regularly and a posteriori do an analysis of this data and decide what the autocorrelation length is, and then use this information to compute fair error bars. I mean, this is the way one should do. What's the question?
How do we sample the tau?
So computers can they can provide a random number. So there are for this it's in general already implemented algorithms that give you a number between 0 and 1. Okay? So you get this number, you multiply it by beta, and so you get something which is evenly distributed between 0 and beta. And so this is how you decide for a new time simply. You can use a USB key which has some quantum optics which gives you a true a true random number. But I think only Matthias Troyer is doing this. Okay? Yeah?
So once we have these two configurations, then the next step would be to develop a new configuration from the Y, right?
Exactly. So the next step here, it's to start from X, you get Y. There are two options. Either you accept the move or you don't accept. If you don't accept the move, then you will remain in X and you'll have to try something else. If the move is accepted, you're in Y. And then you have to go to another one, which might add a new spin or remove one, and so on.
Yeah, but you would be very close to N, right? I mean,
you will be very close. From one step to the other, you're very close.
So, I mean, even though you have a long, I mean, you've run your acceptance ratios for various numbers, as in x1, x2, x3, and so on, you would still be very close to your N. So how do you break out of?
Oh, well, you're very close. I mean, you have all the time. You have a lot of time. So, I mean, you go N, but then you go N plus 1, N plus 3, N plus 4. I mean, you can go away from N, right? It's in principle. So there's no, I can add many of these, and in principle, I can end up in very different places. But the choice, the Monte Carlo will choose where you should go. So it will tell you. So if you want the average, the average perturbation order, it can tell you. It has most contributions come from some. I'm just putting a number 50. Okay, but still the Monte Carlo will move and sample everything that has some weight here, and this goes into quite an ergodic way. But of course, it's many moves, so it's millions of moves. So in the end, you still sample quite a bit.
Thank you.
It's also the position where you are putting, because the matrix would be having a row in different so determinants would be different.
Sure.
How do you choose which position? That means suppose one position fails, or then how to choose the next position?
In general, you just pick it randomly again, and you wait until it's not that small. But you're right. Some choices will be bad. Some choices will because G0 as a function of imaginary time can become very small.
You want an acceptance ratio of 0.5?
I'm sorry?
Don't you want an acceptance ratio of 0.5?
No. No, you don't want an acceptance ratio. No, actually, you would like to have 1 as an acceptance ratio probably. Okay, you would like all your proposals to be accepted, ideally. This would be the best way to sample your space. But you can't, you can't do it.
Isn't it non-intuitive? Because in classical Monte Carlo, what you want is you want to have a 50% acceptance ratio and not 100%.
I don't know. No, I'd be happy with 100%. I'll comment more on this, but to make a long story short, it's in general you don't like acceptance rates that are huge or very close to 1. That's what I mean, because it probably means that you generated something which is so close to what you had before that it's accepted because it's very close. Okay, but it's so close to what you had that if you do steps like this, it will take forever to sample a reasonable part of your configuration space. So in general, you don't like acceptance rates which are too close to 1. But you also don't like acceptance rates which are too close to 0 because maybe they would sample the phase space nicely, but you're always refusing them. So again, it's always a question about finding the middle. Okay, let me move on. We're essentially done. So you want to measure the Green's function. So I think I won't have time to, no, probably not, to derive it completely. But okay, like almost always in statistical physics, the average value of whatever you're looking is the derivative of the partition function with respect to something. In the case of my Ising spins, I could do the derivative of the log of z with some external field, for example, or with respect to a spin, or gives me the average values I want. The same is true for the Green's function. Actually, g of tau, you can show that it's, well, the only difference is a functional derivative, but it's essentially the same. The functional derivative of log of z with respect to delta of minus tau. Okay. I won't carry out the details of this calculation, but maybe I can show you just quickly a little bit why it's true. So the partition function is something which is z. Well, it's my path integral. And remember, I had my action. So my action, it was something like the integral, and there was the non-interacting part. And the thing I had to put here, I had to put c dagger of tau, and I had g0 minus 1 in here. Okay. So g0 minus 1 is my non-interacting Green's function. So I'll leave it blank for now. Plus, there was the interacting part, but it's not important. So g0 minus 1, if you remember, I'll put it in Matsubara frequency. It's I omega n plus mu, this hybridization function here. So that's my exponential. What falls down is c dagger c. So what I'm left with is essentially the average value of the time order c dagger c. And this is exactly my Green's function. Okay. I had to correct this with a minus sign here, but up to this little detail, it's the same story. Okay. So I need to do this on the expression for z, which you remember z. It was z0, and there were all my sums and so on. Okay. So the log here, it will multiply, it will cut this. The log of z will be log of z0 plus log of the sum, and so on. Okay. The derivative of the log of z0, which is the partition function for my interacting system as a function of delta will just give me a G0. Okay? And then here comes the rest. So it's basically something which will be like 1 over, this is why I introduced this Z tilde. Okay, what's left here, this sum which has the determinants here and so on, this is my Z tilde. Okay. So derivative of the log gives me 1 over this, and I have all my sums. So I have my Monte Carlo sum over X. This is the sum over perturbation order, imaginary times, and so on. Okay, and then I have to insert my derivative. So u over 2 to the power n doesn't change. Basically, I'll have to compute the functional derivative of my determinant with respect to delta of minus tau. And there will be my other determinant, which is a different spin. I should have put a spin index here. Something like this, okay? Now, I don't have time to carry out this derivative here, which is a bit of a hassle. It takes a bit of time. So I'll give you the answer, but the idea is basically this is what you have to do. You have to compute this. And you see this is exactly, basically it will be something which looks already quite a lot like my Monte Carlo weight. I have u over 2 times n, d here, so I just hope that carrying this will provide me the information to get back to my weight, which I was sampling, okay? So I'll give you the answer, and I'll write it actually. I'll write it in Matsubara frequencies directly. So G is G0 of I omega n plus, and the second term is G0 I omega n, some function f of I omega n, G0 of I omega n. So the Green's function is something like this, G0 plus G0 f G0. So now I just have to tell you what is f, and we're done. So f of I omega n, this is given by, so let me think, it will be essentially 1 over beta sum over x, and I'll have u over 2 to the power n, and then comes the derivative. I'll have something like, oh yeah, I need a sum over ij, sorry. So there will be a sum over ij. These are the indices of my imaginary times, okay? So these guys run from 1 to small n. I will have dj1 minus 1. So this is what I write here. What I mean is I take in the determinant in the matrix, I take the inverse of the matrix, and I take the element ji. Okay. E to the to the minus I omega n tau r minus tau j, and d up, d down. So that's what I get. I'll check if this is what I should have gotten. I won't make a mistake here. Yeah. Great, that's correct. Okay. So you see, you recognize the Monte Carlo weight in this formula. So when you want to measure this, you see I have this together with this is my Monte Carlo weight. I mean, if I take it in absolute value. Okay. So this means that this is more or less given by a Monte Carlo sum, which is 1 over beta. Okay. And it's my Monte Carlo sum of sum over ij, dj I minus 1 e to the minus I omega n. And you see here, I'll have to be careful. The weight is the absolute value, so I have to correct this with the sign of my configuration x. And I have to divide this by z tilde here, which is sum Monte Carlo of s of x. And this is it. Okay, you can carry out the details. This functional derivative there takes a couple of lines, so I'm not trying to do it here. Okay. What? Yeah, you remember this matrix D was this big, determinant with elements G0 and so on here in there, basically tau I minus tau J. So what I mean here by D, J, I don't take the determinant, but I consider the matrix, I compute its inverse, and I go fetch the Ji element. That's all I mean. I'm sorry? So there's one for up spins and one for down spins. Oh, yeah, sorry. Like always, I forget my spin indices, so there's a sigma here. This is the one associated to sigma. Sorry about this. Almost. I would if this was G. No, this more like this, yeah. So no, unfortunately, it would be nice, but it's already not too bad. I mean, but it's a good point. At least you know what it says is nevertheless that what I measure are corrections around G0, which is already not too bad. Which means when I compute G, I start from G0, non-interacting Green's function, and I compute the corrections around this. So it's already not too bad. Okay, so this is. Yeah, I mean, I might forget most. Okay, well, here I'm. No, usually there's always a D up and a D down.
Below.
Here? Oh, yeah, sorry. There's sigmas all over. Yeah, sure. Okay. Any other question? So yeah, so if there were a sign problem, it would show up here. And like we were discussing earlier, so there's this delta that was in alpha, in the alpha matrices, which will change, which has an influence on the sign. So in practice, for the single orbital Anderson impurity model, you can always, at least I couldn't find examples where you can always tune delta in a way that you don't have a sign problem. Now, there's a little price to pay for this, is that changing delta also changed the average perturbation order of your perturbation theory, and as such also the speed of the algorithm. So there's never free lunch, so most of the time, good sign means slower code, bad sign means faster code.
What percentage of positive signs would be considered not a problem?
Well, this depends very much on what you're looking at. There are cases, I mean, Philippe Werner, if he will talk about out of equilibrium, he could carry out simulations in which the sign was even 10 to the minus 4. And it was still, okay to get some results. In this context, if I have, 10 to the minus 2 as a sign, I'm in trouble. 10 minus 1 is already, well, it's okay, but it's not to be. It depends a lot on what you're looking at. Yeah. No, I mean, there's a way out. I mean, getting the average sign, if you want, the average sign is a quantity which you can compute pretty quickly. You don't have to have tons of statistics. So in principle, you could launch your simulation just to get the average sign out of it. And this would be really, really fast. And that's what you do, or at least what I do, to find a good delta. Okay, so in the beginning, I don't try to measure anything. I just get the average sign, and I tune my delta in a way to have a good average sign. I try to find the delta, which is the fastest, if you want, that gives me a reasonable sign. And then I launch the real simulation.
So if I had negative view, then this issue itself will not.
No, then you would not even introduce alphas. Then you can, actually. I mean, yeah, if you want to introduce a sign problem, you can introduce the alpha.
So physically, what are you doing by putting the delta? Are you introducing magnetic field? I came late, so
you're introducing some a small chemical potential difference between the up and down. But again, I think most of the key for the sign problem is not really the fact that you, well, it's more the fact that you rewrote it as something which is close to 1/2, which is closer to n minus 1/2 times n up minus 1/2 times n down minus 1/2. This is the main thing. The delta is more there to ensure ergodicity and correct a little bit around this. Yes, well, yes. Yes and no. I introduced it here because actually it sort of symmetrizes the Hamiltonian. So I wrote it this way because then your Hamiltonian is more symmetric and the chemical potential shift that you introduce is not spin dependent. I'm not totally obliged to do this. I could also have kept only one of the two terms which I've shown you, okay? It would introduce a different correction to the up and down spins in the chemical potential, and it sort of desymmetrizes the theory, so it's sort of more elegant like this. But it actually, in terms of sign problem, it gives exactly the same answer. So I only introduced it to sort of make things symmetric, but it's not necessary. Any other questions? So you see, we're done. It's a simple algorithm in the end, right? You basically insert, remove vertices, compute these ratios you had on the blackboard, and then after that, compute this function f, and you're done. Okay? So yeah, like I said it already, but the complexity of the algorithm comes mainly from the computation of these ratios of determinants that have an inserted line or column. The way to do this in practice is to use Sherman-Morrison formulas, and this goes as order n squared. So this is essentially the complexity. What else? Yeah, I mean, what comes out in the end in terms of complexity is that the average value, if you want, of n of your complexity, this is something which goes like beta u. Okay, so this also tells you where the algorithm is sort of good and bad. So it's good when these two numbers are small. Okay, so it's an interaction expansion, so you expect it to be good at small u. So the average perturbation order will be low, of course, at low u, and obviously high temperature is always easier than low temperature. I say obviously, it's maybe not that obvious, because you'll figure that for the other algorithm, the hybridization expansion, it turns out that actually high temperature is very difficult. So it's, in that sense, complementary to what Philip will tell you. This works nice at small u, large temperatures, which is actually where the other algorithm doesn't work so well. So they're really complementary approaches. Okay? The autocorrelation time in your Markov chain, you mean? Yeah. As of you. Oh yeah. Oh, so it's sure that the correlation. I mean, the higher these numbers, the longer the autocorrelation time. That's for sure. Okay.
Can you also comment on going to the real frequency with this?
Yeah. So that's what I would like to finish with. It's an analytical continuation. But first, I want to make sure there's no more questions. And indeed, in the 15 minutes that are left. No. So this is all finite temperature. There's beta. Beta is inverse temperature. Beta is what? Well, sorry. No, yeah, you don't want. So this is it. So sorry. You prefer it goes like 1 over u over t. So low temp. I mean. Yeah. So low temperature means, I mean, this guy is going to grow big, so you want large temperature. All right. Sure, and I will. I will. I have a slide with a couple of references about this. Yes. Indeed. So, any more questions on the algorithm? And yeah, I'll give you references, of course. So it is, yeah. Where exactly it comes from is it sort of finds the optimal average perturbation theory, perturbation order. It scans automatically the good perturbation order. And
comment in that direction. Phi is basically the Hirsch phi, you have to cut your times. With Hirsch phi, you have to cut your time axis into slices, and you have to take more slices. The bigger beta times u is basically. So that, and from that point of view, it's very similar here. However, the complexity of this algorithm goes like n cubed in the number of slices. While this one, I think it's n squared or something. So it's faster from the complexity.
Yeah, so basically the average value, all these algorithms, they actually scale linearly. I mean, the average perturbation order scales sort of linearly in these variables. In all cases, in all three algorithms, Hirsch phi, interaction expansion, hybridization expansion. But like, well, you know, Antoine said, sometimes factors, you know, matter. If we had a factor 3 in the TC, would be happy. Here it's the same thing. They're all linear, but the Hirsch phi really goes a lot more like this, and the other two are a lot lower. And when the, like Thomas just said, the complexity goes like n to the cube. So this slope quite quickly starts to matter, I mean, in practical examples. Okay. So one of the issues with these algorithms is, as you by now have seen, the information you get it there, okay, in Matsubara frequencies, okay, or if do the Fourier transform in imaginary time. This is well, nice for the algorithm, but so nice when it comes to computing physical quantities. Sometimes we'd like to have the spectral function on the real axis. And this is the whole problem of analytical continuation. So what we would like is find a way to start from the information of G, say, in imaginary time, and from that get G in the real frequencies. Okay, that's the whole goal about analytical continuation. The problem, it's not easy to do for the following reason. So G, the expression of G of tau in terms of the spectral function is, so I'll try not to get it wrong, it's minus A, the spectral function A of omega, and there are some terms here. This is like this, I think, minus no, I think it's correct. No, it's okay. It's okay, no? Let me check. I think it's okay. It's bad in both when omega is large anyway because of this guy, right? So you can phrase it there. Okay, so yeah, so that's the expression. So you see, this is the expression of G of tau expressed as a function of this A of omega. So this I can write as somehow an integral equation of some kernel K omega tau d omega. Okay, and you can think of it. This is written as an integral, but you could think about this on a discrete grid. Okay, so I could take my G at some discrete points, okay, to get some G at point tau I. And this I can write, so I would discretize somehow the tau i's and the omegas, and this would be a matrix K, if you want, times, of course I missed my spectral function, so this is not going to work. Times A. So I can really look at this if you want as a sort of a matrix equation. G is some matrix times A. Okay, so this is sort of a discretized version of this. Now, in principle, you see, mathematically at least, I could just invert this matrix K and get the spectral function knowing G of tau, in principle. But if you look at this matrix K, the way it works, the way it goes, is that at large omega, the elements are very much suppressed by this term here. So if you want all information in A of omega at omega rather big, is immediately suppressed by this term. Okay? So this matrix here is very ill-defined from that point of view. Computing the inverse is very delicate because all the details of A have been damped, and so this problem is very, very ill-defined. So the whole game of analytical continuation is to try to find ways, clever ways, to start from this and get the spectral function. So Philippe Werner will tell you one of the ways which is quite used, which is called the maximum entropy method, which is one method. I will introduce another method which you will use during the tutorial, which are called Pade approximants. Both methods have their pros and cons, which I will quickly discuss. And with this, I'll finish and can go for a break. So Pade approximants. So the idea is very simple. I'm not sure I will really have time for any details, so I'll really give you the idea, and some of you are interested, I can tell you a little more. Let me find a chart which is a little longer. The idea is to define a continued fraction, which I'll call Cn of z. So this is a complex function defined for a complex variable z. And I define this as a continued fraction. So what is a continued fraction? It's basically something which looks like a1 divided by 1 plus a2 times z minus z1 divided by 1 plus a3 z minus z2 and so on. And I go all the way until I reach the nth, if you want, power, which is basically I end up with 1 plus a n times z minus zn minus 1. It's just the last level of this staircase. Okay. So this is called a continued fraction, and the game is the following. So this is a function which is defined everywhere on the complex plane. Okay. So if I could have this function, I could use it as a sort of a fit. So from my Monte Carlo, I do get information of G, or of the self-energy, at the Matsubara points. These are just points somewhere in the complex plane. Okay? So this I know. So I would like to find a way to say that at this point, at the sort of number of finite of these points, this is the same as my continued fraction Cn taken at I omega n. So say for all n that range from 1 to n. Okay. So basically the game is what is, I have to find the coefficients a1, a2, and 3, an, in order to have this condition satisfied. If I were just telling you this like this, you'd say, okay, but this doesn't look so easy, because this continued fraction, I'm pretty sure things will become very sensitive. You know, when I change my a, which is all the way down there, you know, things might be quite difficult to actually tune in a way that this works. But the nice thing about these Pade approximants, or this continued fraction, is there is actually a recursive way to set this precisely in a well-defined manner. So it's not a fit. It's not I'm trying to play with my parameters and sort of minimize a function to find the a1 to an. There's a well-defined procedure to actually get my a1 to an. Okay, so these are Pade approximants. Yeah. So I'll come to the pros and cons. Let me just quickly finish here. So once you have this, so once you have found the set of a1 to an, this function here is completely defined all over the complex plane. So then I just get the spectral function, or G, at omega or sigma. I could have done this on G, doesn't really matter. But once I have a Pade approximant, let me do it this way then. Sigma just above the real axis, then I just evaluate my Pade approximants here. You know, if I have the information about A1, AN, and so on, I can compute this anywhere. So this is how I get the spectral function, or the Green's function, or the self-energy along the real axis. Now, where is this good and where is this bad? So the positive thing about this is there's not so many knobs to do it. Namely, the only thing you can play with is how many of these points in the complex plane I'm going to use to actually construct my Pade approximants. That's actually the only knob I have. All the rest is completely defined. Okay, so this I would say is a positive thing. You'll see in the Maxent there are more knobs, many knobs. Now the negative thing about this is nothing, if I try to do this on the Green's function, it's just fitting a complex function by another complex function. There's nothing in the formalism that, for example, tells me that I will get a positive spectral function. Okay, there's no constraint about this. In Maxent, there is. But here, you'll get, if you try to do this on the Green's function, you will get spectral functions that become negative most of the time, somewhere at least. So where is it good? It's actually only a method which is good at very low frequency, but at low frequency, it's really good. It's much better than any other method, at least I know. So if you try to get a spectral function, in general, that there's a low energy range where the method is actually quite reliable and gives you correct answers. And they're typically, for the kind of problems we're interested in, it's sort of the range of the, it's more the quasi-particle peak, say, this kind of energy scales, okay? What I'm trying to say here is, while you can certainly sort of have a good resolution for the resonance, for the quasi-particle peak, what you certainly cannot describe with Padé approximants is any kind of structure in Hubbard bands here. What will happen most of the time is actually that the thing starts, being negative and so on. Okay, so this you have to keep in mind. It's a very good method if at low energies, but at higher energies, it will give you quite crazy results in general.
But is it that on the negative frequencies you get positive, and the problem comes from the positive frequency?
No, it might happen on negative frequencies as well. Oh yeah, sure, it just anywhere.
Is there understanding why it works well near omega equals 0?
Well, I think the sensitivity of this function, yeah, yeah, and this remains in the continued fraction.
Works well on the negative side of the thing. Because there the kernel would be 1, right?
Oh, negative side, you get this guy who kills you, so. No, the thing is suppressed on both sides. So you're dead. No, there's actually been a lot of work around the Padé approximants and the origin of the sign changes. One can actually even formulate the condition of having a positive spectral function in terms of the A's. But the condition is so difficult to impose that in practice you don't do it. But there's been a lot of work around this.
So what is the range that you would guess it would work in, for example?
In practice, the way I do things with Padé approximants, like I said, there's just one control parameter, which is how many of these Matsubara frequencies you basically use to get your Padé approximants. So what I generally do is I start with 10 points and then do 20 points and then 30 and 40, 50 and so on. Okay? And for all this, I will get a different answer, of course. But visually, just looking at the curves, there's in general a range of frequencies where the curves pretty much fall on top. And this is where I would say, okay, I trust my Padé because I can play around with more or less Matsubara frequencies and I get things that don't change so much, so I trust my result there. And anything else, I just don't trust. So.
The problem with Padé, right? The number of points you take as it increases beyond a point, you start getting infinity. So if you use the recursive formula.
What's with the recursive formula?
No, if you start, beyond n equal to some 50, 100 even, you get the coefficients to be infinity. So how do you...
Oh, so the n, the Padé approximant you want to use here. So the n here should be the same n as the number of n's you want to fit this to, okay? So there's a non-ambiguous definition of all the a coefficients if the order here n is the same as the number of points you want to have this condition for, okay? Now it's still a fragile decision. These coefficients, the recursion is quite sensitive, so you actually need to have many decimals. So you need to use some package which has a flexible number of decimals, because nevertheless the procedure can become unstable, but you can control it.
For getting finite frequency responses, for example, by convolving 2 of the A's, that means I will also be restricted to looking at finite frequency responses to some window.
Sure. Yes. Any other questions? I think my time's up, but that's pretty much what I wanted to say. What I wanted to do still is give you a couple of references. Marcus, I don't know if you can plug your computer, which will answer your question, which are a couple of references for both. I mean, you gave one already, the Houston on the impurity models, but I have a couple of papers for the impurity models. In the meanwhile, any questions still on these issues? Yeah, I need the screen to. Framework which allows you to quite easily write scripts, write DMFT self-consistencies, write equations involving Green's functions and self-energies. And the game tomorrow will be to get familiar with this, to write your own IPT solvers. It's just, it's one equation, so you'll have to implement this. And then you'll play around, get spectral functions using Padé approximants, look at the Mott transition, and then maybe it's, see how the critical U might depend on some variables in a multi-band system. We'll see how we go. No, I want the last page of this guy. Well, maybe while you browse through, yeah, okay. These are the references. So, well, this Thomas already gave, but I think it's a beautiful book. It should be. Whoa. So that's for tomorrow for the tutorial. For the day after that, and okay, great. For the two other tutorials, we'll have two options, I think, but we'll see how that goes with timing. But one will be to go and compute a true LDA plus DMFT calculation for strontium, which one? Vanadate. And so starting from Win2K and do DMFT on top of this. For some motivated guys, like I said last week, if some of you really want to go ahead and try to implement the interaction expansion solver, I'm happy to do this with you. But if you want me to really help, it would be good if you have C++ background. Otherwise, it will be a little difficult. But so if there's a smaller group of motivated persons, I'm totally into trying to do this with you. You'll see it's fun and it's not that difficult. So yeah, sorry, I kept this, but just to show you the curves. So this is Hirsch-Phi, the average perturbation order, and these are the new algorithms here. This is for a quite unfair set of parameters, at least for the CT int. So anyway, it's quite lower, and this is how the typical distribution of the diagrams as a function of perturbation order. So you see they're distributed a bit like this. So only diagrams around some quite peaked value contribute, and then at higher order they don't contribute. Anyway, so Padé, with Padé is not that bad. So if you push your data far enough, and this is a bit the state of the art. Sorry to take some more minutes here. This is a comparison between doing NRG, which was presented by Thomas before, and which is which gives you information directly on the real frequency axis, and doing CTQMC and doing some Padé on top of it. And you see, I mean, it's not that bad. You can do many things. I was telling you that it's completely impossible to get the Hubbard bands right. Okay, so now you tell me, but look, this works quite nicely. Well, first of all, it's because NRG also doesn't get the Hubbard bands right. This is the first reason, and the other reason is you in general you don't do Padé on the Green's function, but you do it on the self-energy. Okay, and then you use, either, for example, the DMFT self-consistency to reconstruct the spectral function from there. So this hides somehow part of the noise is hidden by this reconstruction. So you get, this is the imaginary part of the self-energy. So you see, you can really, with Padé, really get quite nice information here, and even this kink, which Antoine has shown to exist here. It's really nice results. So yeah. Anyway, just about references. So this is quite generally on quantum impurity problems, a beautiful book. I really recommend. About CTQMC solvers, so there is a review of modern physics by Emmanuel Gould, which presents everything. And these are more the original papers. Here are by Rubtsov for the interaction expansion. Here by Werner and Millis. Another paper of Philippe here on the hybridization expansion. Well, you probably all know this, but this is the review by Antoine on DMFT in general. So if you want to know more about DMFT, this is a good starting point. And there are several, there's probably more than this, but these are some open source codes to get a solver, a CTQMC solver that's Trix. So that's the one we developed in the Paris region with Marcus and others. And there's, for example, also Alps and our competitor, say. But there are, of course, other codes around. So if you want to write this down, it might be useful. Anyway, with this, I thank you for your courage and attention. And come anytime, ask me a question. I'm around.